We're going to talk about some of those accessories that we install along with the pump and how it makes the pump more reliable, a better fit for the customer, a better answer for them. Uh, we'll see that it also helps the longevity of the pump. It really helps the pump last for the customer. So we'll talk about many of these. We're not, of course, not going to talk about each and every possible accessory that there really could be. These are going to be ones that we use commonly, the ones that you see repeatedly on the skids. The engineering department, that pre-mounted skid package, it really came out of the need for many of these accessories. Before we know it, we're talking to the customer, we're telling them how these accessories can help them, and we've talked them into really a skid package, and now we have the opportunity to plumb all of this together the way it's supposed to fit together for the customer. So I think it's a really nice presentation. Now the customer has a simple inlet to hook up, so between their day tank or their bulk storage to the skid, they can really get a contractor to do something like that. And then from the discharge of the skid to the process, again, that contractor is very capable of doing that. But we have everything on the skid now, all of those accessories, they're installed in the proper order, and I think it makes for a very nice package for a customer. But why do we need those? Why do we include those? It's just not, it's not just a rep for us. It helps the pump be a metering pump, and we'll talk about that as well. So this slide is just a really brief overview. Again, this tells us how these accessories are going to help the pump be a metering pump. Metering pump, it is that we want that pump to be repeatable. Each and every stroke of the pump should be the same volume for the customer. If the pump isn't seeing the back pressure regulated, then pressure and flow tend to be inverse. Or flow can go through the pump. That check valve is going to prevent it from coming back through the pump in the opposite direction, but it will all day long allow flow to go in the, we'll call it the forward direction. So it can siphon through. If we have a head pressure pushing through there, we don't have anything preventing it on the opposite end, it can push into the system or into the process unregulated. So we don't want that. Pressure relief, of course, that's a safety issue for us. So now the system may demand more pressure than what we have our back pressure valve set to. The pump will continue to pump, providing it's rated higher than what we have it set to. And then since the system is already above what we have the back pressure valve set to, we've achieved that pressure. The back pressure valve is open. We're pumping through it, and now we're achieving the pressure that the system demands. Well, we want to limit that. So now we've essentially established a minimum pressure that the pump is always going to see with the back pressure valve, and now we're achieving a maximum pressure that the pump is going to see with the pressure relief valve. So those are very critical things. A pulsation dampener, we'll talk about that early on in this presentation. It's very important to us. Particularly the larger volume per stroke that we're dealing with, it becomes more and more important, and we'll see why. The gauge. Setting those back pressure relief valves, we can't guess at that. We want to know what those back pressures are. Gauge, and we always include an isolator with that gauge. Many times the chemical that we're dealing with, the chemical that we're pumping with the pump, isn't compatible with the material that the gauge is made out of, whether that is stainless steel or maybe nickel-plated brass or something like that. That can go away very easily if we don't separate the chemical from being in contact with that gauge. So that gauge isolator is very important as well. An injection valve, that prevents backflow, provides some back pressure. We'll talk about that. It also helps prevent the line from being diluted, and we'll talk about how critical that is as well. So we'll get started here, and Pulsation dampener. This slide is trying to show you a system, and we've all seen systems probably very similar to this. So we have a very long discharge run. It has a lot of bends in it. As we accelerate that, as the pump's on the discharge part of the stroke, we accelerate all of the fluid in that line between the discharge of the pump and the injection point. We start that in motion. Now we create inertia. That is a mass, that volume becomes a mass in motion, right? It wants to stay in that forward direction. It wants to continue on. Now the pump comes around on the suction stroke, and we're pulling that discharge valve ball down into its seat. We're trying to put it into check. We're trying to stop that forward flow of that volume, that mass that we have moving in the discharge line. And if that mass is enough, if we have enough inertia there, hold up that diaphragm, we can hold that valve ball from being closed, and we can actually cause damage inside of the pump, because now the cam follower is off of the cam. It's anticipating when to come back on, but it gets released very suddenly, and the cam's coming around in the opposite direction to now create another discharge stroke, and things start slamming together at not the most opportune time. So that is a very bad thing for us. That cavitation, where we have the flow going in one direction, we're trying to pull back on it in the opposite direction, that is a cavitation for us, and that is a very critical thing. Again, the volume per stroke, the larger that is, the more important for us. So now the longer the discharge run, we have a larger volume that we're dealing with, even if it's a smaller pump. So we have to be very aware. We don't want that long of a run on the discharge, and especially when we get into pumps that are rated with a higher volume per stroke, we want to start very much insisting that a pulsation dampener is one of the critical items that we include with it. With that pulsation dampener, it needs a regulated back pressure. If the back pressure that it sees isn't regulated, it has a hard time helping the system away from that cavitation issue. So you can see this graphic modified the one previously, but now we're including the pulsation dampener. And you can see the top half of the pulsation dampener, it's charged with air or a gas, depending on what pressure we're dealing with. We have a gas charged in there, whether it's just air or some other gas in the top half. And that's contained in a bladder, and it's separated from the fluid at the bottom. So now when the pump goes on its discharge stroke, some of that volume, some of that fluid is absorbed up into that pulsation dampener, and it's going to compress the air and the gas. Gas is compressible, that fluid is not. So we're going to compress that gas. We're going to build the pressure of that gas inside of there. Some of our flow is going to go out towards our process down the piping stream. Now when the pump goes on its suction stroke, the pulsation dampener is going to relieve that pressure in the bladder. It's going to force that fluid that we absorb on the discharge stroke of the pump back out, back down towards the process. We can't go down towards the pump. We have a check valve there. So now we're helping that check valve closed the way it's supposed to. We're only stopping the flow between that T and the pulsation dampener. So that amount of volume, that inertia that we have is very minimal there. So now we're not going to cause the damage inside of the pump. So that is one thing that will help us. It's not always the ultimate answer. We can't solve the world's problems always with a pulsation dampener. But it is one thing that we have to consider. Sometimes we actually have to change the diameter of pipes and whatnot. So we can, but with this accessory, this is going to help us by far have to do that. So I think it's a very, very critical accessory for us. You can see the arrangement here. The way the pulsation dampener should be installed is in direct line with the discharge valve of the pump. We like that flow to go directly up into, hit right into the bottom of that bladder that's inside of that pulsation dampener. And then you can see on the left at the top is our back pressure valve. That back pressure valve is going to dictate the pressure that we're set at, and then we're going to charge the gas in that back pulsation dampener to 90% of what we have that back pressure valve set to start at. We would need a gauge in line. That gauge is a helpful tool here as well because we can see the pulsation on that gauge. So if it continues to pulsate a lot, even if we're charged to 90%, we can very carefully, very slowly bleed some of the air, some of the charge out of that bladder to help smooth out that pulsation that we might be seeing. So it's a good slide to show where it's installed. So regulating the back pressure, this is kind of a cutaway view of the back pressure valve, what you might see. One of those is the inlet, we'll call it to the left. Now that would be oriented a little bit closer to the center. So it's going to come in the center, and then the one on the right being the exit is going to be towards the outer edge of the diaphragm. You can see the diaphragm indicated. Then we have a spring above that, and we have a diaphragm hub. That diaphragm hub kind of takes so that spring isn't pushing directly on the back of the diaphragm. So now the force required to open that diaphragm is our pressure that we're going to generate with the pump. So now it has to push against that spring. To make it require more pressure, we're going to want to pre-compress that spring. So to do that, we simply adjust that adjustment nut down further. It's threaded, so we thread it down in further, and it's compressing that spring. So now we're going to have to push up on that diaphragm harder with more force, that's our pressure, to open it up so that we can flow through. So that's nothing more than that. Now, a back pressure valve, this is a 2-port device. Now, we do commonly use a 2-port, a back pressure valve, as a pressure relief as well. We just have that installed before the back pressure valve, and we adjust it higher than what we have the back pressure valve set to. So now it's the pressure relief in that case. We'll see some graphics showing that as well. Right here, in fact, this is a simple lift system. We have the pump on top of the tank. You can see the weighted foot valve. We'll talk about that. That's an additional check valve we have lowered into that supply. And we come up to the 3-port now, pressure relief valve, and it's relieving back into the tank that's below that. Above there, you see the back pressure valve. So we're keeping a pressure between the discharge of the pump and that back pressure valve. We're keeping that very regulated, very consistent between those 2 points. We're adjusting that with the gauge just below that, and then the pulsation dampener is in between there on this particular application. So that back pressure valve is also going to help prevent a siphon. And that siphon can actually be created if we have pressure in that line, if we consider that blue line our process flow at the top. If we have pressure in that line, but there's a significant amount of flow, we have some velocity in there, it can still create a lift. It can actually pull the chemical below, up through the pump, into the process if we don't have that back pressure valve included. So we try to achieve with that back pressure valve, we try to achieve around the kind of general rule of thumb is 15 psi higher on the discharge than we have on the inlet. And sometimes we have to take those negative pressures into account, such as I just mentioned, that velocity of flow in the line can create a negative pressure. So here we're pumping below grade or below where the supply and where the pump is. And of course, that's 101. That's how we create a siphon. So now we have a back pressure valve all the way over close to the injection point. So we have to be careful, again, not to create a siphon. Sometimes some regulations insist that we have 2 back pressure valves, and they want to be ultimately sure so that it doesn't, that chemical doesn't siphon into the process. In this case, Fluoride into drinking water is one example. Depending on where you're at in the country, sometimes that regulation is to have a redundant back pressure. The pressure relief valve is very similar. So as we mentioned, we're establishing with the back pressure valve, we're establishing a minimum pressure that the pump is going to have to pump against. Now, if the system exceeds that, the pump is going to continue to pump because we're already opening the back pressure valve up to its maximum pressure. But now we want to establish a maximum pressure. So if we control those two things, if we control that pulsation, we're going to get nice, reliable, repeatable, and we're going to get nice longevity out of the pump as well. We're not going to destroy the pump. It's going to last a long time. Even that, it'll help the diaphragm on the pump last that much longer as well. You can see here, again, we compress that spring to require a higher force, a higher pressure to open that diaphragm so that it goes out the third port at the bottom. On a pressure relief valve, the 3-port device, the inlet and the outlet, which are 180 degrees apart from one another on the left and right, you can see those. They're not directional. Either one could be the inlet, either one could be the outlet. The inlet and outlet on the back pressure valve are a little bit more directional. So as long as we have that relief is that bottom port in this slide. Here you can see another variation of what I talked about. We're using the 2-port, truly a back pressure valve. It comes off of the T. We're using that as our pressure relief. So we simply adjust it higher than the back pressure valve, which is the very top valve that we see in this display. We have it adjusted higher than that slightly. So now if the system pressure exceeds, we can still pump into it up to where we have the pressure relief set to. Now that's going to open and it's going to feed back into the suction line. So that pump is going to stop building any more pressure into the system. So that's very critical to us. Alternatively, the 3-port device, which is again below or before, if you will, it's before the back pressure valve, it comes off and it goes back into the supply tank in this case. We don't have it going back into the suction line, but into the supply tank. So either are acceptable. Quite often on our skids, you will see a second back pressure valve, a 2-port device, coming off of the T and going back to the suction line, just like you see here. Another example now in a suction lift application, it's kind of the same thing. We have the 3-port device that's going to relieve back into the tank. In this case, we're going to relieve back into the tank with the 2-port device as well. So either can be used in either application, and you see some arrangements here how we would potentially do that. Chances are you're not going to see 2 pressure relief valves on one system. I don't remember seeing an application where we've done that in the past. We talked about back pressure, pressure relief. Those can be provided by the multifunction valve as well. The back pressure that the multifunction valve provides is fixed and it's pretty minimal. It's only 22 psi, where a typical back pressure, pressure relief valve, those are both adjustable up to about 150 psi. We can even get ones that are adjustable higher than that, but the most common ones are up to about 150 psi. So the back pressure is fixed on the multifunction valve. The pressure relief is fixed as well, but there is a variety. The back pressure is 21 psi typically, and the pressure relief, there's a couple different levels depending on which pump and which range of pressure relief we wanted to include with them. One of the other things that the multifunction valve can do for us, we can manually open that pump to atmosphere or back to the supply tank, and that's going to help us with priming. So another function of that is kind of helping us with priming without really coming in contact with that chemical that could potentially be a pretty nasty chemical for us. The weighted foot valve we talked about, it's an additional check valve, so you do see the ball check seat there, the check ball. The seat is below the valve ball, of course, allowing the flow to go up through but not come back down. So once we've lifted that fluid, we don't have to lift it again. It's going to continue to progress up towards the pump. At the top, you see the tube fitting. That thread at the top, remember, is going to be metric, but that doesn't matter because with our tube fitting, our compression fitting, or our connector set as we typically describe it, that's what's important for handling the dimensions of the tubing. And we have those where we can always handle standard size tubings that we find here in the States. So that's not a problem. Below that check, we do have a mesh screen to keep solids out. So if you do have a chemical that may have contamination in it from time to time, you will have to clean out that mesh screen, so keep that in mind. The other thing you see at the bottom, it's a ceramic weight. So this foot valve, not only does it help us keep the pump primed, but it also helps keep that tubing nice and vertical down in our supply tank with that weight. If the chemical that we're pumping is, for example, fluoride, we know that fluoride isn't compatible with ceramic. It will etch that away, it will go away. So we have to replace that ceramic weight with, we have PVC weight to offer, and that's right in the catalog, right in the accessories section of the catalog. So we can easily supply that for you. The injection valve we talked about, it's a spring-loaded check, so we need a force again to open this to push the chemical past it. And that spring is fixed. It's providing about 7 psi of back pressure. We need 7 psi of force to open that to push the chemical past. So you see again our connector set, our tubing, our compression fitting is at the bottom here. That's the inlet. Then we're going to thread that. You see the NPT thread at the top. That's going to go into our injection point. Okay. Then we don't want the chemical necessarily to just go into the pipe and go along the sidewall of that pipe. That's where we have the slowest flow in that pipe. That's where we have the most friction. The flow is going to be slowed down in the set along the sides. So we want to get that chemical out into the center a little bit. So we have that quill or that nipple that sticks out into the flow, and we can cut that to length. So we want it to get out in as close to the center of the pipe, or at least as far away from the edge of the pipe as we can possibly do. Okay, this will prevent flow from coming back into the line between the pump and the injection point, or the back pressure valve in the injection point. We don't want to dilute that chemical because now we don't know what the concentration is. And if we're trying to dose versus off of volume and end up with a particular concentration, and we don't know what that starting concentration of our chemical is, we just can't control it. So this is a very important device for us. One other accessory you'll see very commonly on a skid is a calibration column. Historically, people have done this. It's nothing new with a metering pump. They're going to take the calibration column and time it and do a drawdown test. We do that on the suction side of the pump. We can't pump back into the calibration column and get a good representation of what the pressures are in our system. So we can't pump into the calibration column to do that calibration test. So we want to do it off of the inlet, or it's going to provide fluid to the inlet of the pump. And we want to size that for at least 30 seconds of drawdown. Now with our pumps with a digital display on them, the Gamma L, the Delta, and the Sigma control versions, all of those have calibration features to them. And what I mean by that is we can do a drawdown test. We're not keeping track of the time. The pump is counting the number of strokes, but we put in the volume that it drew down in that number of strokes, and it's going to do simple math to calculate what the volume for each individual stroke is, or per stroke. So once it knows the volume per stroke, it can extrapolate out if it knows how many strokes per hour it's going to do, and it can actually display the flow rate in either gallons per hour or liters per hour, depending on how we've calibrated. So to do that routine, we want to know a true volume number. So we want that calibration column. We're going to pay attention typically to the milliliters in graduation on that calibration column. I put a little note to the right there where we're sizing it for 30 seconds. Gallons per hour, if you take what the pump is rated for in gallons per hour and you multiply by 63, it's the magic number, 63, that's going to give you the milliliters in a minute. Okay, so gallons per hour times 63 would be milliliters per minute. 63 is, there's 3,785 milliliters in a gallon, and if we divide that by 60, I think we should be pretty close to that 63 number. So that's where that 63 comes from. But gallons per hour times 63 will give you milliliters in a minute. Okay. We also have level switches. In this case, it's a two-stage. We also have some single stage for some of the other pumps. But a two-stage level switch, you'll see at the very bottom that rectangle is the float. So we would suspend that so that it's just above the foot valve. The intention there would be we want it to reach the bottom stage, the tank empty stage, and it stops the pump before that level gets below the foot valve. That way it stops the pump from losing prime. So we suspend that slightly higher, and that can trigger the relay output on the pump. So now we can know about it being empty or being to the point where it has stopped the pump. Above that molded part, you see just a little weight, so it's going to help it keep towards the bottom of the tank. Because remember, we do have a float there. We want that to float in that fluid so that we know when it goes below there, it's going to float, or it's going to lower and hit that stage on that particular switch. We also offer flow monitors. Metering monitor is what I've always known it as. It's labeled flow control, and personally I don't like that label. We're not controlling the amount of flow with that, so I think that's a little misleading personally. I like to call it a metering monitor. That's what I knew them as when I started, and still refer to it as that. So if you're ever talking to me for any reason and I say metering monitor, this is the device I'm talking to. But what this device does is it verifies that after the pump stroked, it delivered a volume out of the discharge. We don't necessarily know what that volume is, but we deliver enough volume that we can actuate this device if we've set it properly. And every time we change the volume per stroke, the stroke length is what controls that. We have to change that adjustment on the front of this metering monitor. So now that feedback goes back into the pump, and the pump knows when it discharged. It expects that signal back from this device in a timely manner. If it doesn't see that signal come back, it starts counting the number of consecutive strokes without that feedback, and it will put the pump into a fault after that predetermined number. You can see you can adjust that up to 125 consecutive strokes without feedback before the pump goes into a fault. So if we're pumping and we missed 80 strokes, and then all of a sudden we get one with feedback, we have to go 125 again before we put the pump into a fault. The default number on that is 8 strokes without feedback, and I would probably recommend, so that you don't get nuisance alarms, you probably shouldn't go below that number 8. It seems to be a pretty solid number. But we can go as high as 125. Some people will ask us if we can extend that beyond 125. We can't in the programming of the pump. However, what you can do, and we could do that for you with our panel shop, is we can have it open the pause contact on the universal control cable. So we would open the connection between the black and brown wire, so the pump goes into a pause mode briefly. Then we reconnect that, we short those back together so the pump comes out of the pause and it goes back to run. So when we recycle that pause contact, it starts the pump over and resets that 125 number. So now we're going to run another 125 consecutive strokes before we go into a default again. Remember, 125, that might sound like a lot of strokes, but if we're talking about a gamma L pump, 180 strokes per minute maximum, if we're running at that maximum speed, that's less than 1 minute of runtime. So we're not missing that much flow necessarily into the system before we're notified about it. So sometimes, especially if it's a chemical that off gases, we want to give it a chance to off gas before we consider that the pump going into full. So that's a brief overview of some of the accessories that we would have with the pump. Hopefully that has helped share some information with you there. If you have any questions, let's use the GoToMeeting toolbar. It has a questions tab on there, and just type that in there. So let's see, we had some audio issues in the beginning. Everyone hears me. Steve mentions you can talk about ratio on some columns. Ratio, calibration column, on some of those, they're labeled, it will say a certain flow rate for so many seconds of testing. I think that's what Steve is alluding to there. So it'll say gallons per hour for a 30-second drawdown test. And that's good. That's good if you're doing a manual test where you're actually timing it. But if you're calibrating the pump, again, we need to pay attention to the true volume number. So the milliliters on that calibration column is a little bit more important to us in that time. But I think that's what that ratio that Steve might be referring to there.